Let's dive right into the first problem on the 2026 AP Physics C Mechanics exam. Definitely a challenging one. So we're told that a box of mass m slides to the right on a horizontal surface. A small cube also of mass m is inside the box. We see that the cube is pressed against the right wall of the box above the bottom, so it's not touching the bottom of the box. And we're given the coefficients of static and kinetic friction between the cube and the wall as mu s and mu k. Now, we're told the speed of the box is decreasing as a result of a resistive force that is exerted on the box, which we can model as Fr equals negative dv, where b is a positive constant and v is the velocity of the box. But other than this resistive force, which we can assume is sort of air resistance, friction between the box and the horizontal surface is negligible. Then at time t equals 0, we're given our initial velocity. Then up until t critical, we maintain our current state of the box being in contact with the right wall, but not in contact with the ground. At t equals t critical, we start sliding downwards such that eventually we hit the ground. So before we dive into part A, a couple of things to just note going in. Obviously, this is going to be a dynamics problem of some sort. We'll be wanting to think about F equals ma. And then because we notice an air resistive force where we've got F is equal to negative bv, we do want to have in mind F equals ma is equal to dv by dt. We might be expressed is equal to mdv by dt. In other words, we do want to have in mind that maybe we'll want to set up a differential equation. Maybe we'll want to use separation of variables. So that's all in the back of our mind as we jump into part A. So in part 1, we're asked to determine an expression for the magnitude of acceleration of the cube and to express our answers in terms of m, fn, and any physical constants as appropriate. And so I'm going to try not to overthink this. We're being asked for the acceleration of the cube, so let's consider what forces act directly on the cube. Well, there's probably going to be a vertical force of friction. There's going to be a force of gravity. We're not being asked about this, but these presumably balance each other out prior to t critical when we're vertically in equilibrium. And lastly, the box is moving to the right at the start with speed v0. There is a resistive force on the box, which means the box will be slowing down. And what that means is that our cube is sort of being pushed into the front of the box, such that the box pushes back with a normal force Fn. So that's my free body diagram. And then importantly, whenever we draw a free body diagram, we want to indicate our direction of acceleration, which in this case is to the left, because that's the direction of our resistive force, which is slowing us down. So now a direct read of my free body diagram along the x-axis is that Fn is equal to the mass of my box times its acceleration. I'm looking for acceleration. Therefore, A equals Fn over m. Pretty easy free points for that first part, and that will happen on occasion. So moving on to part 2, we're asked to derive an expression for Fn as a function of time from t equals 0 until immediately before the cube reaches the bottom of the box. Okay, express your answer in terms of those. Begin your derivation with a fundamental physics principle or an equation from the reference information. Okay, fundamental physics principle, probably F equals ma is a good starting point. And this is where our suspicions from earlier that maybe we'll want a differential equation might come into play because we're asked to express Fn as a function of time. But let's dive into it. We know that Fn is equal to ma, but of course, A is an unknown, and now we're being asked to solve for Fn, so that alone is kind of insufficient for us. And so what I'm going to consider now is my system equation. I'm going to look, and at this point, I can consider either my system equation for the entire system or my equation for the box alone. But since we're looking to solve for Fn, I don't want to involve Fn as an unknown in my second equation. So I'm going to look at the system equation. If we look at my system as a whole, so here I've got my bigger box M, I can treat it as a system with total mass 2m, a resistive force going to the left, which is Fr, balanced vertical forces, so we're not going to worry about that. And there's no friction with the ground. So Fr is our only horizontal force. And so I can state that BV, which is the force of air resistance, is equal to 2ma. And so putting this together, our goal is to solve for Fn, which means that we'd like to know what A is. The mistake to make here is to say BV equals 2Fn. Note that V is a function of time, and we don't actually have its value. We do know V naught, but we don't know V of t. And so our goal now is going to be to solve for A or V, which necessitates setting up our differential equation. So we'll state that BV is equal to 2m dV by dt. And now we can do separation of variables. So this gives us that dV is equal to BV over 2m dt. I'll divide through by V. So dV over V is equal to B over 2m dt. We go ahead and integrate. And of course, we want to be careful here because I've made a careless mistake with my signs. Note that A is negative while V is positive, so I don't want to replace A with dV by dt, but rather with negative dV by dt. So let's not drop that negative. And so what we have now is that ln of V is equal to negative B over 2m t plus C. Now, personally, at this point, what you would need to do is go ahead and solve for C. I personally find that a bit tedious to do. So what I'll do instead is solve this via direct integration. If you're not comfortable with that, then just go ahead and solve for C. But I'll do my definite bound. So I'm going to state that at t equals 0, my speed is v naught, and I'd like to know my speed at a later time. So what this gives me is that ln v evaluated from v naught up to v is equal to negative bm b over 2m t evaluated from 0 to t, which tells us that ln v over v naught is equal to negative b over 2m t. Note that on the left-hand side, I use the property of logs, right? So it was ln v minus ln v naught. Okay, now I exponentiate. V over v naught is equal to e to the negative b over 2m t, and therefore v is equal to v naught e to the negative b over 2m times t. Definitely take a moment to pause the video, make sure you understand this derivation for separation of variables before I go ahead and erase it. Okay, so now we know what our velocity is. And so we can solve for our acceleration as a function of time as well. We can state using equation 2. Obviously, we have two methods here, right? We can choose to differentiate this, right, and get our acceleration, or more simply, we can plug into equation 2 such that b v naught is bv naught e to the minus b over 2mt is equal to 2ma. And so now putting this together with equation 1, we know that Fn is equal to ma, but I'm going to replace a with b v naught over 2m e to the minus b over 2mt. Should be careful with where my t is located there, right? Not in the denominator. And there we have it. We now have Fn expressed purely as a function of m, b naught, v naught, and t. So in part 3, we're being asked to sketch a graph of the magnitude of force of friction exerted on the cube by the wall as a function of t. So this is where it's important to recall the start of the problem. So from t equals 0 up to t critical, our box is not moving vertically. We are in equilibrium. And so that tells us two things. One, sum of forces in the y direction will be 0. And two, if important, we're in the realm of static friction. Then, for t greater than t critical, well, greater than or equal to all state, that is when we are no longer in equilibrium, we're sliding down the wall, and we're dealing with kinetic friction. And so a trap one can easily fall into by considering T less than T critical is to start writing down Fn and attempting to use mu s Fn. But remember that force of static friction is less than or equal to mu s Fn. And so the more important principle here is that we're actually unmoving. And so what's going to happen is that up on T critical, my forces are balanced. So we have force of friction up. This is just pulling from our earlier free body diagram. Mg down, obviously Fn to the left, but our forces are balanced. And so we've just got a horizontal or a frictional force, which is balancing out gravity. And so we can label this Mg. Now, critically, we can now sort of think ahead and realize that, okay, Fn is steadily decreasing. So eventually force of static friction can no longer match the force of gravity, and that is when T critical occurs. So we end up in the realm of kinetic friction. Well, if we're in the realm of kinetic friction, then we can explicitly write out that force of friction is equal to mu k Fn. And as we've seen earlier, Fn is exponentially decaying, and so we can just sketch an exponentially decaying graph. You don't need to get that exactly right, but that is what we have past T equals T critical. Moving on to part B then, we're asked to derive an expression for T critical in terms of MB, mu s, V naught, and physical constants. This is exactly what we were foreshadowing in the previous part. If we consider the box of mass M, we know that we have a vertical force, Fn, at force of static friction, which is less than or equal to mu s Fn, and a downwards force, which is mg. And so all we need to state is that, okay, mu s Fn at the point at which we are about to start falling, static friction is completely maxed out. Saturating the inequality, it is equal to mu s Fn. So we'll set mu s Fn equal to mg. Now we pull our earlier information, which is that Fn is equal to bv naught over 2 mu s b v naught over 2 e to the minus b over 2m times t, and set that equal to mg. And at this point, all we need to do is solve for T critical. So we have e to the minus b over 2m times T critical is equal to 2mg over mu s times bv naught. Take the natural log of both sides. And so we end up with b over 2m. T critical is equal to ln of 2mg over mu s times bv naught. And at this point, fairly straightforward algebra. So we get T critical is equal to negative 2m over b ln of 2mg over mu s bv naught. Let's indeed do a very quick intuition check on this, which is to say I'm going to quickly rewrite this without the negative out front. So T critical is equal to 2m over b ln of mu s bv naught over 2mg. What would it take for this answer to make sense? Well, we would need our term in the ln to be, right? We would want our ln to be overall positive. For ln to be overall positive, this requires mu s bv naught to be greater than or equal to 2mg. So what does this actually mean? Let's divide through by 2. And what this statement is saying is that our initial force of friction, mu s times Fn, must be greater than or equal to mg. In other words, this is simply requiring that in the initial state, we be held up by static friction.